Okay, ji, welcome back. Let's wait for a minute so that the rest of the people they can also join. Okay, ji. So before that, we have started with the transistor. In the transistor, we have said that for the normal operation of a transistor, the emitter-based junction need to be forward bias and the collector-based junction needs to be reverse bias. And with that, we have separately shown that what happens with the emitter-based junction once it is forward bias, and the separately we have also shown that what happens when the collector based junction is reverse biased. And then we have taken a look of the combined overall effect of the emitter based junction and collector based junction once they are forward and reverse biased. And with that, we have seen that we come up with the equation that IE, which is the emitter current, is actually equal to the sum of the base current as well as the collector current. Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
ठीक है जी. And then we have also seen that the collector current is basically the summation of the majority carriers as well as the current which is flowing due to the minority carriers. So we said that the collector current is basically equal to IC majority plus IC minority, right? So this we have done in the first session. Okay. So now what we see that if we take a look of this combination and we replace this with its symbolic representation in the circuit, how we are going to get the circuit now? Let's take a look. So if we incorporate the symbolic representation of the circuit, so we will have something like this. We say this is emitter, so this means this is E over here, this is P over here, and this is C over here. And then we are applying the forward biasing to the emitter base junction, and then we are applying the reverse biasing to the collector base junction. So we have got this VEE and we have got the VCC. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, Ji. So if you want to see the current which is flowing in the circuit, so or here we have IE that is flowing, or here we have the current which is flowing over here is IB, and over here we have the current which is flowing over here is IC, right? With this we can say that if you see this circuit can be divided into two portions. One is this side, which is incorporating the emitter base junction, and this side is normally being taken as the input, and this side over here, which is incorporating the collector base, this is being taken as the output side of the circuit, right? As well as if you see, there is an input current which is flowing over here is being taken as IE, and the input voltage in between the emitter base junction, it will be taken as VBE, which is in between the base and the emitter of the transistor. Similarly, we have at the output side, we have the collector current, which will be taken as the output current, and the output voltage will be in between the VCB, which is in between the collector and the base of the transistor. Are you with me?
Yes, sir.
Yes, sir.
Okay, Ji. So with this, what we can see that we can have the input characteristic curves as well as we can have the output characteristic curves of this particular circuit. Now, at the input side, we have the input current, which is IE, as well as we have the input voltage, which is VBE. So if we want to plot the input characteristic curve for this circuit, so we can draw something like this. The input characteristic curve input characteristic curve that is in between the input current, which is IE, and the input voltage, which is VBE, which is in between the base and the emitter of the transistor. Now if you see, we started with the for the normal operation of the transistor, the emitter base junction need to be forward bias, right? So how this curve is going to be? Anybody? Can you hear me?
Yes, sir. We can hear you.
Okay, so how this curve is going to be? How this curve will look like?
tightening to increase the exponential.
जी क्या कहा आपने?
सर ये करो exponential increase of current, i.e.
Okay, let's get back to the circuit. If you see, this is the circuit, or if we go into the internal diagram, it is over here. So this is the one, right? So in the internal diagram, we have said that the base emitter junction need to be forward bias, right? And to be forward bias, this means that the emitter base junction over here, will only conduct once the barrier potential is going to be overcome, right? So if this transistor is made up of silicon, so what is going to be the barrier potential for silicon?
0.7.
0.7.
0.7 volts, right? And if it is made up of germanium, it will be
0.3.
0.3.
0.4.
0.3 volts, right? So normally the transistor, they are made up of silicon. So again, getting back to the input characteristic curve over here, right? So we say that the curve in between the input current and input voltage will be something like the curve for the forward bias diode. Are you with me?
Yes, sir.
Right?
Yes, sir.
So if I say over here it is, I say it is 0.7 volts, right? So this means before 0.7 volts, the curve will be along
0.
the horizontal axis, and once it overcome the 0.7 volts, the curve will be something like this for the actual diode. But if we go with the practical one, so it is at 0.7 volts. Normally we say it is a straight line, right? And if we say it is behaving as an ideal diode, so for the ideal diode, it will be along the axis, because in case of ideal diode, we say it works as a short circuit switch. Are you with me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right? So if we consider it as a practical diode, so it will be somewhere here. And if we take it as the actual diode or the piecewise linear curve, it will be somewhere here. So if we say it is a piecewise linear model, the curve will be somewhere this one. And if we say it is the practical one, practical model or the practical diode, it will be somewhere here, right? So depending upon which model we are considering, so we can say that it will be behaving according to that specific model. So this means the input characteristic curve will be before 0.7 volts, it will be somewhere here, and after 0.7 volts, it will be behaving something like this. Are you with me? Or if we
Yes,
consider
sir.
as more as of the actual one, it will be something like this, right? So this will be our input characteristic curve, which is in between the input current IE and the output voltage VBE, right? Yeah, sorry, the input voltage VBE. Now if we go towards the output side, so towards the output side, we have this circuit, which is the output side of it. We have IC as the we have IC as the output current and VCB as the output voltage, as well as we also know this thing that we previously discussed, that IE is equal to IB plus IC. But we know this thing that IB is very small as compared to IC. So what we concluded, that IE is almost equal to IC, because IB is actually in the range of microamperes and IC and IE, it is in the range of milliamperes. So let's suppose, to make the output characteristic curve, we actually deal with the output current IC and the output voltage, which is VCB, right? Now what we want to see, that let's suppose if I say that the input current is IE is equal to 0. What does this mean? If I say the input current is equal to 0, IE is equal to 0, what does this mean? Anyone?
So emitter
There is
current is short circuit.
AC will just will equal to 0.
They're open
no
circuit
output.
emitter.
So this means that we are in a situation where we have the circuit which is something like this, that there is no forward biasing of the emitter base junction, right? So if the emitter base junction is not forward biased, so in that specific case, IE will be equal to 0, right? Are you with me?
Yes, sir.
So how I will become equal to 0? This means that VEE, the biasing source which is being connected to the input circuit, VEE is not making VBE forward biased, right? So if VBE is not forward biased, so in that specific case, the emitter current will be equal to 0, right? And once the emitter current is equal to 0, this means the collector current will be only dependent upon, if you see, IC is equal to IC majority plus IC minority. So this means we do not have any majority carriers which are available in that portion of IC, right?
Yes.
So this means IC will be only dependent upon IC minority, right?
Yes, sir.
And in that specific case, when we look into this circuit, so this means that this current which is flowing over here, it is IC, which is flowing over here, is only due to the minority carriers, and this current over here will be taken as, we can say that this is equal to 0 plus I 0 plus ICBO. Now, what does this mean? This means that it is that specific portion of the IC which is flowing through the collector base junction when the emitter circuit is open. Are you with me?
Yes.
Okay. When IE is equal to 0, IC will be equal to that portion of the collector current which is flowing through the collector base junction when the emitter is open. ICB means it is the current which is flowing through the collector base junction, and this O over here means that when the emitter is open. Emitter is open means that there is no current which is flowing in the input circuit or the emitter circuit or IE. Question? G. Question? Okay, G. So IC will be equal to ICBO. ICBO means it is that portion of the collector base junction in which the emitter is open, right? So this means we can go back to the characteristic curve and we can say that this current, as it is due to the minority carriers, and the scale over here is, if you see, it is in the range of milliamperes, and this current which is flowing due to the minority carriers is actually very small current which is also in the range of microamperes. So this current over here will be almost at the same level as the horizontal line over here, right? And this current over here, due to IC, it will be called as ICBO, right? It will be called as ICBO. It means it is that part of the collector current which is flowing through the collector base junction when the emitter is open, right? Now, if I say I go back to the circuit, and if I say I go back to the circuit over here, and if I say I make this VEE variable, so this means if I make VEE variable, so this means if I increase the biasing potential of the input circuit VEE, and I also install some resistance because I do not want to damage the circuit. So I add RE over here, and I also add RC over here in this circuit, so that when the voltages they increase, the currents they will also increase. When the currents increase, so we want to limit the current and the voltage and the resistance drop in the inside the circuit, so that the transistor should not be damaged, right? So when we are increasing this voltage, so this means we are increasing the value of current inside the circuit, right? So once we increase VEE, so this means due to increase in VEE, the current, i.e., let's suppose it increases to, I say it increases to, let's suppose from 0, it increases to 1 milliampere, right? Once this increases to 1 milliampere, so we also know this thing from our previous knowledge that IE is almost equal to IC. So if IE goes to 1 milliampere, so on the output characteristic curve, if we say IE is equal to 1 milliampere, right? So if I mark on IC axis 1 milliampere, so what is going to be the value of IC over here? Anyone?
1 milliampere.
So it will be almost equal to 1 milliampere because we have the equation which says IE is almost equal to IC. So this means the value of IC will also be somewhere close to 1 milliampere when IE is equal to 1 milliampere. Are you with me?
Yes, sir.
Similarly, if I increase the voltage at the input side, if I increase the voltage at the input side, which is VEE, so I increase this voltage so that I am able to increase this current to 2 milliamperes, right? So if I am able to increase this to 2 milliamperes, so going back to the circuit, if IE is now equal to IE is equal to 2 milliamperes. So if I mark this 2 milliamperes over here, so this means IC will also be somewhere close to 2 milliamperes, right? Similarly, I increase IE to 3 milliamperes, so this means IC will also increase to somewhere close to 3 milliamperes. Are you with me?
Yes, sir. Bilkul.
Yes, sir.
Okay,
Yes,
if you see, the horizontal axis has got the voltage VCB, right? So this means if we increase or decrease the value of VCB, the curves, they are more or less constant. Why? Because if you see over here in the circuit, we are providing this VCC, and this VCC is providing the, if you see this one, we are providing VCC over here, and this VCC is providing positive potential over here. So this means whatever the majority carriers, they are being emitted by the emitter, they are being collected by the collector over here, right? But if I change this value VCC such that this VCC or this positive potential is no more positive over here, right? So this means if I am decreasing this value VCC so that this is no more positive over here, so this means the majority carrier which were being emitted by the emitter, they will not be collected by the collector, right? So this means the potential between the collector and the base VCB will no more be positive. And if it is no more be positive, so our the curve, if we go back to the curve, the output characteristic curve over here, so this means if we are at this specific point, so we are reducing the value, and if we are reducing the value, it goes up to here, it goes up to here, right? So this means at this specific point, it is now no more attracting the majority carriers which were being emitted by the emitter. And if we start decreasing, so this means they will decrease and they will get down to 0 over here. Are you with me?
Yes, sir.
Yes, sir.
सर
No,
रिपीट
sir.
करें जरा सर ये तो
Okay.
जीरो से इधर है लेफ्ट साइड
जी
से है ना
जी 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 बिल्कुल.
तो ये तो मतलब इसकी पोलैरिटी चेंज हो जाएगी
तो जब आप पोलैरिटी चेंज करेंगे तो जो मेजॉरिटी कैरियर्स पहले अट्रैक्ट हो रहे थे वो अब रिपेल होना शुरू हो जाएंगे, और जब रिपेल होना शुरू हो जाएंगे तो दिस मींस द करंट विल गो डाउन टू 0, right?
यस यस सर
Right, so previously we, if you see this axis, this is increasing, but this side, if I go back and I go back in this direction, this means after 0 it becomes negative, right? So at certain negative point it will go back and it will die down. So this means we won't be having any current over here that is
सर
flowing.
अगर वीसी
जी
सर अगर वीसीबी की स्ट्रेंथ ज्यादा करेंगे तो चाहिए तो ये था कि इंक्रीज होना चाहिए था कलेक्टर करंट
देखें, आपको यही तो मैं बात समझाने की कोशिश कर रहा हूं कि the point is we have this equation. If you see, we have this equation, IE is equal to IB plus IC, right?
यस सर
And IE is almost equal to IC. The reason is that the base current is in the microampere range, right? Now, once this is the case, so if you increase the value of VCC over here, if you increase the value of VCC over here, that can only attract the number of majority carriers which were being emitted by the emitter. It cannot get something more from the emitter if the emitter has not emitted the majority carriers. It can only collect the number of majority carriers that were being emitted by the emitter, as well as some of the few of the minority carriers they were generated by the base. So it collects both of them, and that's it. So what I'm trying to say is that the collector will only collect the majority and the minority carriers emitted by the emitter and by the base or at the collector. So it cannot get something more from it. So therefore, if you see the curves of the output characteristic curve, it is almost flat over here. That this means that if IE is 3 milliamperes, so IC will be close to 3 milliamperes. Similarly, if IE is 2 milliamperes, IC will also be close to 2 milliampere. Similarly, if IE is 1 milliampere, IC will also be close to 1 milliampere. So the reason is that it cannot get more because the emitter is not generating more if you increase or decrease the VCB as long as VCB is positive. But if VCB goes in the negative direction, then the collector won't be able to collect the majority carriers which were being emitted by the emitter. And therefore, if that is the case, we will have the IC current that will go down and go to 0 over here. Are you with me?
यस सर
Right?
Yes, sir.
So if you see, the transistor has got the normal operation of the transistor occurs when we have the linear curve. So in the linear curve, the region is basically if the emitter base junction is forward bias and the collector base junction is reverse biased, right? So this is the region, in which we have the emitter based junction is forward bias and the collector based junction is reverse bias. This region is called the active region. Are you with me? If the emitter based junction is forward bias and collector based junction is reverse bias, that region of the output characteristic curve is called active region. Now if you see, when we are moving in the horizontal direction after the axis, after this axis, so what happens, that the collector based junction is no more reverse bias, right? But after this axis, the collector based junction becomes forward bias, right? And once the collector based junction becomes forward bias, so we comes into another region for this curve, which is over here. This is this region, and this region, if you see, it is called saturation region, in which the emitter based and the collector base, both the junctions, they are forward biased. Are you with me?
Yes, sir.
Right? So the emitter based junction and the collector based junction, both are forward biased. That region of the curve is called saturation region. And if you see, there is a third region over here, that the region which is below the horizontal axis, this region, the region which is below the horizontal axis, this region over here, in this region, if you see, the emitter based junction and collector based junction, both are reverse biased, right? And this region is called the cutoff region, right? That once the both the junctions both the junctions are reverse biased, this is called the cutoff region. The session is going to end in less than a minute, so we will restart in 10 minutes time. ठीक है जी? So we will restart from this point again.
Okay.